Hey people, welcome back to Code Covered. In this video, we are going to solve today's daily question from Leetcode. And the question is, count the number of subarrays with odd sum. I hope that you guys have given this problem a read, and I also hope that you guys have tried to solve it on your own because that is mandatory. And yeah, with that being said, let's just now look into the problem. As we can see here, the question title itself is self-descriptive. So it basically says that we will be provided with an array, and our job here is to figure out the count of all the subarrays whose sum is actually going to be an odd sum. So this is what pretty much the question is expecting from us. Now, there is a question from my side. Think that or consider that there are no constraints for this problem as of now. Think that there are going to be no constraints as of now. If this is the case, then what would be the most brute force approach that we would be thinking through? It is going to be O of n square approach, right? Let's take the same array. So in this O of n square algorithm, we will be just considering each and every index as its own starting point of the subarray, and we will be gradually incrementing the window size one by one. And finally, we will be updating the result by checking the parity of each and every window sum, right? So basically, I will be starting from 0 and going till n, and j will also start from I and it will also go till n. Now finally we will be just incrementing the window sum by the array elements, and post this we will be updating the result by checking the parity of this particular window sum. Let's say there is a function here passing the window sum. It will say whether this satisfies the condition or not. Basically the condition is this, right? So this is pretty much all about the brute force solution. But if we take a look at the constraints which are given in the problem, it actually says that n can go up until 10 to the power of 5, which means O of n square will result in 10 to the power of 10, which is 100 times greater than 10 to the power of 10. Sorry, 10 to the power of 8, right? So, which is definitely not the expected time complexity, and thus this solution is not gonna work. So, which also says that the question is actually expecting a solution which runs in a linear time complexity. Whoa, that sounds difficult now. Honestly, guys, this problem is a difficult problem because I have seen a lot of medium problems which are marked medium and a lot more easier than this particular problem. That is why I just generally don't believe the question difficulty markers which are given in Leetcode. Okay, so initially, honestly, I was also not able to figure out any optimized solution for this. Basically, I was also stuck in the brute force approach, was not able to figure out a way to move further than that. But again, after an ample amount of trial and error dry runs, I was able to finally pick the click, and I solved it in O of N approach. And here I am recording the video to let you know the exact approach that I followed. So I will be showing the exact dry run which I followed to solve this problem in a couple of minutes. So before that, let me also give you a short intuition behind this problem so that you will also be parallelly building the solution while I teach. Let us now take a bigger array. And in the previous brute force approach, we just tried to fix each and every point as a starting point, and we went on searching for a proper ending point, and we incremented the result accordingly. Now, what are we going to do is that we are going to try to invert our thought process. So by inverting the thought process, I mean that instead of fixing each and every point as a starting point, here now we are going to fix each and every point as the ending point. And we are going to figure out all the subarrays that are going to end at this particular point, which are going to be valid. Valid in the sense their sum is going to be odd. So now you may ask a question that how this is going to work, because this is very much similar to the brute force solution, right? Exactly. If we follow this solution exactly the way I said, it won't work. I agree with you guys. But this kind of thought process, this kind of inverting the thought process will actually help us build a solution that is going to run in a linear time complexity. So let us now quickly discuss the crucial observation that is eventually going to help us build this linear time solution. So let's say there is a number n, and this number can be either odd number or an even number. I have also taken an example 49 and 50. right? Now the question is, I should have to remove a number from 49 such that the resultant number is also going to stay as an odd number. So this is the concept. This is the question. So what could be this number x? Can I say that no matter what number this x is going to be, if this is going to be an odd number, if x is going to be an odd number, can I say that the resultant will always be an even number, right? So let's take an odd number like 49 minus 3. What is 49 minus 3? Here 49 minus 3 is going to be 46. This is going to be an even number, but we don't need this, right? So can I say that no matter what this x is going to be, if it is going to be an even number, now while removing this even number from 49, we would obviously be getting an odd number as the result, right? Let's take an example for that too. So 49 minus an even number, let's say 4. So here 49 minus 4 will be 45. So yeah, we are getting an odd number as the result. Now let's do the same for even number as well. So let's say we have to remove a number from 50 such that the resultant number is going to become an odd number. Initially it was an even number. Now the result has to be an odd number because this question is rounding up uh, around the odd values only, right? So that is why. So yeah, no matter, can I say that no matter what this number is going to be, if this number is an odd number this time, can I say that the resultant will always be an odd number? Because in this case, the initial number is going to be an even number. Let's take an example. Let's take 50 minus, give me an odd number. Let's take 3. So what is 50 minus 3? 50 minus 3 is going to be 47. It is an odd number now. Let's take one more example. So 50 minus 7. Now this is going to be 43. Again, this is going to be an odd number. So yeah, we just have seen a crucial observation that is really going to help us building the linear time solution. Now let's see how to put this into use. Let's take this bigger subarray. Now what are we going to do with this bigger subarray is that we are going to fix each and every point as the ending point, and we are going to calculate the number of valid subarrays that are going to be ending at that particular point, right? So let's just fix index 4 as the ending point such that it is at the last point, so that we'll be having multiple examples to explore, right? So yeah, now if we just fix index 4 as the starting point, now first of all let's calculate the sum of the whole subarray that is ending at 5, which is 1 plus 2 plus 3 plus 4 plus 5, which is going to be 15, right? Now let's say we have initialized a variable result and initialized it to 0. Now we can see that 15 is an odd number. So the sum of the whole subarray is going to be an odd number. So we can very well increment the sum, increment the result right away from here, right? Because the sum is going to be odd and we need odd subarray sums. Now what are we going to do next is that we are going to go and remove each and every prefix sum, each and every prefix subarray sum, and we are going to check whether the remaining subarray has a sum that is still going to be an odd sum. So if that is not clear, let me just repeat it. What are we going to do is that we are going to go and remove each and every prefix subarray from the bigger subarray such that we will be checking whether the remaining elements are having a sum that is still odd. Now, does this concept ring any bell? Right. Let me just say how exactly am I going to do that. Then you guys try to relate it. How are we going to put this concept into use? Right. Now 15 is the whole subarray. Now let's try and remove one from it. Now 15 is an odd number. If we remove a sum that is going to be an odd number, will it result in an even number or an odd number? It will definitely result in an even number, right? So that is what is being said in this concept. If the bigger number is going to be an odd number, and if we remove an even number, then we will be getting an odd number. But here, this is going to be an odd number, right? The sum is going to be odd. So 15 minus 1 is going to result us with 14, which is an even number, but we don't need this, right? So yeah, now let's check for the next window. So in this window, what is the sum of this window? The sum of this prefix subarray window is 3. So 3 is an odd number. So again, we need an even number. So this is not a valid prefix subarray sum to negate it with 15. Let's just check it once. So 15 minus 3, it is going to result with 12 as the result. Now again, this is going to be an even number and this is also not valid, right? So let's just move on to the next window, which is going to be 1 plus 2 plus 3. Now 1 plus 2 plus 3 is having a sum of 6. Now this is falling into the place, right? So we need an even sum and we just have gotten it. Now let's just check it. So 15 minus 6 is going to give us a result of 9, which means it is odd, and here we are going to increment our result, right? Now this is an interesting case, right? And yeah, now let's go to the next window. So 1 plus 2 plus 3 plus 4. So now this is going to be having a sum of 10. 10 is again even, right? So let's check here. So 15 minus 10 is going to give the value of 5, which is again odd, and this is what indeed what we need. So result plus plus. So from this, what are we trying? What am I trying to imply is that if the bigger subarray sum, and see, before saying this, we don't have to increment the window from 1 to 5, because if we negate the prefix sum starting from 1 up until the end of this bigger subarray, then the sum will be 0, right? So we also don't want 0. So that is why it is better to start from 0, and it is better to stop until I minus 1. So 0 to I minus 1. Cool. So with this, what am I trying to imply is that if the bigger subarray sum is going to be odd number, then if we somehow add the count of all the even prefix subarray sums, let's call it EPSs. So if it is odd, if the bigger number is odd, we need the count of even prefix subarray sums, right? If we had this count, then we can simply increment result value with this count, right? Instead of iterating at each and every point and calculating the sum all along the way that we iterate and increment it one by one, if we just have this value up front, then we can just simply add it in the result by O of 1, right? And also, don't worry, how are we going to do that and all? It is just a piece of cake. Trust me. I'm just trying to make you guys understand the critical concept that is running behind this problem. Okay. And the code is just simply like 4 to 5 lines code. So right now, just forget about it. And I'll also uh, give a proper dry run on how to do this in O of n as well. So don't worry about that. Yeah. Now, if the bigger sum is odd, we need to have the count of EPSs. EPSs means even prefix subarray sums, right? Now, if it is going to be an even, if the bigger subarray is going to be an even sum, then we should need the count of odd prefix subarray sums. You can very well refer that from this observation which we have already discussed, right? Now let me just give you the proper dry run of O of n approach, and after that we'll be just jumping into the code. So in the previous explanation we have seen the calculation of answers, I mean results, for the last index alone. In this example, in this dry run, we'll be fixing each and every point as the end point, and let's see how to calculate answers for all of these endpoints in just one pass, right? So yeah, for that we need some variables to be initialized. Obviously, result variable is indeed needed, and this big sum is going to depict the sum from zeroth index up until to the ending point, so 0 to I, right? And EPS's count, as we discussed, it is going to be the even prefix array sums up until starting from 0 to I minus 1, right? And OPS's count is going to be odd prefix array sums starting from 0 to I minus 1, right? With that being said, let's just start the try run. So here, let's fix 1 as the ending point. If 1 is the ending point, then what is going to be the big sum? The big sum is going to be the whole subarray sum. Now it is going to be 1. So if it is 1, initially EPS's count or OPS's count and all will be 0, right? In fact, let me also put it as 0. Now, when we just start the iteration and fix 1 as the ending point, right now bigger sum will be becoming 1, right? Now, what is the next step? We'll be checking if the bigger sum is actually odd or not. If it is odd, we will be just right away incrementing the result, right? That is the very next step. So right now we can see that this is going to be an odd number. So we can just directly increment our result by 1. So after incrementing it, we will be now checking for the EPSS count and OPSS count according to the parity of this whole sum, right? Now, what is the parity of this whole sum? This is an odd number. So come back to this explanation. So if it is an odd number, we need the count of EPSS, right? And right now the count of EPSS is 0. So we don't have to add anything to the result, right? So we can very well move to the next end point. But before moving to the next endpoint, can you also see that this particular prefix subarray sum can act as an odd prefix subarray sum for the upcoming endpoints, right? So why don't we just increment OPSS count by 1 before going to the next pointer, right? Because for when I is going to when this point is going to be the end point, then there is no OPSS count for this or EPSS count for this. But for the next point and all, this point will be acting as the prefix sum, which is having an odd sum, right? Of course, then we should have to update the OPSS count before going to the next point. So let's just do that. We just have updated the OPSS count to be 1. Now our ending point is at 2 right here. So if our ending point is at 2, what will be the bigger sum? It is going to be sum from 0 to first index, so which will be 3 here. So if the sum is 3, then yeah, we can right away increment the result count because 3 is going to be an odd number, so result will be 2 right now. And if the bigger number is going to be odd, then we need the counts of EPSS. But here again, EPSS is still 0, so we don't have to add anything. So again, before going to the next next endpoint, we should have to update the OPSS count because this is an odd sum, right? So let's just update the OPSS count. Cool. Now let's go to the next endpoint. When this is going to be the endpoint, the bigger sum will be 1 plus 2 plus 3, which is 6. Now what is the next step? 6 is an odd number, so we can't increment the result at the next step, right? So now we should have to check for the EPSS count or OPSS count. Now 6 is going to be an even number. If 6 is going to be an even number, then we should have to definitely check for all the OPSS counts. And we indeed have some OPSS counts, right? So let's just add that OPSS count to our result. So 2 is already there in the result, so 2 plus 2 will be 4, right? And before moving forward, we should have to update the EPSS count right now because 6 is going to be even. So let's just update our EPSS count to be 1. Now going to the next ending point. Now when 4 is going to be the ending point, the bigger sum is going to be 10. Again, 10 is even, we cannot increment our result. So the next step is check this table. So if it is an even number, we need OPSS counts. And what is the OPSS count so far? It is 2. So let's just increment it. 4 plus 2, it is going to be 6, right? And yeah, before going to the next position, we should have to update either EPSS or OPSS. Now, this is an even number, so we should have to increment EPSS, right? Now, going to the next position. Now, what is the bigger sum? The bigger sum is going to be 15. Now, 15 is an odd number, so we should have to, we can definitely right away increment the result at the next step. Okay, we are done with that. Now, if 15 is an odd number, then we should need EPSS count. What is going to be the EPSS count up until this point? So it is going to be 2. So 7 plus 2, it is going to be 9, right? And yeah, this is going to be the last iteration. So even if we update the EPSS count and OPSS count, it doesn't really matter, but let's just give it a proper ending. So 15 is going to be an odd number. So we update OPSS count by 1, and then the starting point goes out of bounds, and the final result is going to be 9, right? Now exactly, let's just see how to do this in code. But did you actually understand the power of observation, right? And that's why I initially said that this question is not going to be that much of a straightforward question. And yeah, this is one of such patterns which was also new to me. So try to just save this question and try to revise all such common questions which are asked in Subarrays. Try to add this also as a part of such question, right? Let's just go to the code now. Now let's try to initialize the variables that are needed. So big sum is going to be 0, and EPSS count is also going to be initialized as 0, and so will be OPSS count, and obviously result. So result is equal to 0. Now we are going to iterate for each endpoint in the array. So for each endpoint, what is the very first step? Very first step is to add the prefix sum. So prefix sum will be going into the big sum. Big sum will be having the sum of all the array, sum of the whole array starting from 0 to I, right? So yeah, let's do that. So endpoint. Now there are two cases henceforth. So case one, when big sum is actually odd. This is a case, and case two, when big sum is going to be even. So let's tackle these both cases. So when big sum mod 2 is not equal to 0, which means it is odd. So whenever it is odd, we can just right away increment result variable by 1, right? Because as we have discussed, a big sum is going to be odd, then it is also a valid subarray. So we can increment the result by 1, and then we can add the contribution of EPSs. Because big sum is even, so we have to add the contribution of EPSs. It's vice versa, as we have discussed in the table. When n is odd, n is even, which number we should have to remove to get the odd number and all those things. Yeah. Now after this, big sum is odd, so we should have to increment the contribution of OPSs, right? Because big sum is odd. So let's do that as well. So OPSs plus plus. Now again the same steps, but without this step, without line number 15, the same steps, but vice versa. So result plus is equal to, now big sum is going to be even, so we should have to add the contributions of OPSs to it. So after that, big sum is even, so we have to increment the contribution of EPSs itself, right? And why are we not incrementing result on the first go? Because when big sum is going to be even, this step is not needed, right? Because it is not a valid subarray. The bigger subarray is not going to be a valid subarray. That is why we are just adding only the odd prefix subarray sums contribution. And as big sum is going to be even, we are going to be incrementing the count of the EPSs right from here. So that's it. That's pretty much it. So let's return the result. So let's try to run it. And also the question has given us to use mod. As we can see, all the test cases have been passed. So let's just add mod as well here. So mod is equal to 10 to the power of 9 plus 7. So at each iteration, uh, after incrementing the result, let's just simply do result mod is equal to mod. I guess now it should be working fine. Yeah, as we can see, we also have gotten a good beat percentage. Yeah, with that being said, let's just wrap up the video. I hope that you guys have gotten enough knowledge to solve this question. Cool. Guys, one last crucial information before wrapping up this video. So there are some fixed variations among subarray questions. Among those, these are some of the variations. Let's say the first variation, sum of all the subarrays. This can be solved by a method called contribution method. It's a very beautiful method. And find subarray sum, which is equal to k. This one we can solve by using 2 pointers, and the same question basically, but with negative elements. In that case, 2 pointers probably won't be working. So we should have to tweak a bit, and we will be using a combination of prefix sum plus hash map to solve this problem. And maximum sum subarray. So this question is a famous question. I guess probably you guys would have already known this. So here we will be using a Cadane's algorithm, right? And I have added today's question also as a new variation, because this question seemed a bit observational, and I kind of liked this question. So yeah, subarray with given subs with given parity. So this one we'll be using EPSS. We have used EPSS OPSS plus prefix sum, right? So the beauty is all of these algorithms are going to run in linear time complexity, guys. If you want me to make dedicated videos for each of these variations, please do let me know in the comment section. So with that being said, I'm dropping off. It's Arvin signing off.